Hi, so the last type of induction that we would have to do with Pure Core 2 extends this idea of your induction of inequalities that you met in Pure Core 1 that the previous video has tried to recap. So again, it's sort of going to extend it with summation and with maths that you hadn't met in year 12. So the idea is still the same. You're going to have factorials, you're going to have inequalities, but it's going to bring in all sorts of things that you've since met that you hadn't met in year 12. So here's the first example. So first example, and again, this would be classed as an A2 example, but again, I think, you know, lots of you would have had a good go at this in year 12. So the first bit, and I'm going to remember that I am going to hold the pen really close to the end. So first of all, find the smallest integer of n such that n factorial is greater than 2 to the n. So when I first did this, I thought, oh, I'll use table function. And I rearranged it to make it n factorial, take away 2 to the n is greater than 0. And I've set it up in table function. And obviously it happened really quickly. So essentially you could do something like, you could put 3 in and maybe, it says find. If it said show that, you might have to justify your answer a bit more by maybe putting 3 in and show that it doesn't work and then putting 4 in. But because it says find, it just wants the answer. And you know that 4 factorial is greater than 2 to the 4. You know, 24 is greater than 16. And if you put 3 in, 3 factorial is not greater than 2 cubed. So your smallest integer of n is very definitely 4. So part B, and now you've got your proof, which is obviously a bit more work. So what you're going to do is you're going to prove n factorial is greater than 2 to the n for n greater than or equal to n, and obviously in this case it's going to be n greater than or equal to 4. So this is what we're wanting to prove. N factorial is greater than 2 to the n, and that's going to be where n is greater than or equal, well, I didn't mean to do all that rubbing out, so 2 to the n where n is greater than or equal to 4. So again, the first thing you would do is your base case. So your base case. So you have n is 4. So 4 factorial is 24. And 2 to the 4 is 16. Of course, 24 is greater than 16. That's a greater than. I'm slightly off the page there, aren't I? So it's greater than 16, therefore holds for n equals 4. And what you would then do is you would do your inductive step. So you assume that k factorial is greater than 2 to the k, where k is greater than or equal to 4, and you need to show that k plus 1 factorial is greater than 2 to the k plus 1. So that's what you need to show. And again, right, I'm just gonna delete that. I think what I have been doing is I've been sort of boxing those off. So let's have a little look. So we know that k plus 1 factorial is the same as k plus 1, k factorial. So we know that k plus 1 factorial is greater than k plus 1 times 2 to the k. Now, I know what I want to show here is that k plus 1 factorial is greater than 2 to the k plus 1. And this is how it feels a little bit like with an inequality, because it's just got to be greater than, or it's just got to be less than. Almost feels like a little bit of a fudge. Now, I know if I was to come back here, I know that another way of writing that is k plus 1 factorial is greater than 2 times 2 to the k, if I sort of rewrote that out in another form. So essentially, I've just literally got to show here that k plus 1 is greater than 2. K plus 1 is greater than 2. And of course it is, because k is greater than or equal to 4. So I've shown it, haven't I? I have shown. So we've then got, so we've shown, so what have I shown now? I have shown that k plus 1 factorial is greater than 2 to the power of k plus 1. So I've shown it. So what you would now have is your statement, you know, your conclusion, your induction conclusion. So you would say, and again, we've got them in here. So what we would do here is would be the exact same thing, but it would be for n equals 4. And so that would be your statement of conclusion. It's the same thing. I've just literally replaced that 5 with that 4. So, however, this is a question taken from a cross-topic review test in the book. And I've actually got a video on my YouTube channel that I made, I think it was May 2019, for not last year's year 13, the year 13 before, the year 13 that I actually sat the further maths exam. I've got a video doing this, and I think it's all about part A. A student has emailed me to say that she's stuck on this, an extremely able student, and so there is a video out on this. So if you want a bit of a challenge, prove the first bit by induction, and again, obviously it's all about the inductive step. If you know, so stop this video now, because I'm going to go through it. Stop this video if you want to challenge yourself, and then see how you get on. Right, I'm now going to prove the first bit. So of course, the first thing you're going to do is your base case. And so your base case, hopefully, you know, really straightforward. You can see that this is a summation. So I'm going to write this as going from r equals 1 to n. And you can see that we have got the sign. And if I look at my general term, it's 2r minus 1 times theta. Okay, and my base case is going to be when n equals 1. So what I'm going to do here is just find my first term. So I know that on the left-hand side, when n equals 1, I'm going to get my first term, which is just sine theta. On my right-hand side, when n equals 1, I'm going to get sine squared times 1 theta all over sine theta, which of course is going to be sine theta. So it holds. Right, and now what we're now going to do is we're going to prove this by induction, and to do that I'm going to move over here. So what I'm going to do for my inductive step is I'm going to assume, so I've first of all written the left hand side as a summation, which, you know, is a little bit of work in itself. I'm going to assume the sum from 1 to k, and again I'm going to use the general term. And I'm going to assume that that is equal to the sine of k theta all squared all over sine theta. And what I need to show is the sum from 1 to k plus 1 sine is equal to this. Okay, that's what I need to show. So this is going to be, it's going to involve a lot of maths. Okay, it's going to involve quite a lot of maths. And I'm just going to see if I can, make that a little bit. Can you see I haven't done, that's not been my best circling of the thing that I need to show. That's what I need to show. And it's going to be a little bit of work, okay? Are we ready? So the first thing I'm going to do is I'm going to rewrite this summation. So I'm going to do that in black. So I know that the sum of k plus 1 from r equals 1 of the sine 2r minus 1 theta is going to be the sum of the first k terms plus the k plus 1th term. Now, I know from what I'm assuming, the sum of the first k terms is this. So that's okay. I'm fine with that. So that's going to be the sine squared of k theta. And I'm going to add to it the k plus 1th term. And I know that my general term is this. So I'm just going to have my general term with the r replaced with k plus 1. So I'm going to add on the sine of 2 k plus 1 minus 1 theta. And what I think I'm going to do, because I'm a little bit afraid of this, is I'm going to, I've dropped a sine there. I'm so sorry, that's got sine theta on the bottom. Thank you. What I'm going to do is I'm going to put this all over sine theta, and I'm going to when I multiply this by sine theta, I'm also going to expand this bracket. So I'm going to have the sine of 2k. I'm going to get plus 2 minus 1 in there. So plus 1 theta times the sine of theta. Okay, now my phone is starting to not like this. It's gone into low power mode, but I think it's still recording. Yeah, right. So I'm now going to step outside the question, and I'm going to think about some identities. So I'm going to think about some identities. So I'm going to step outside. So the first identity I'm going to think about is the cos of a plus b, which I know is cos minus sine minus sine. I know the identity. I'm going to have the sine of a plus b, which I know is the sine of A, cos of B, plus the sine of B, cos of A. I don't know why I've done it that way around, but I have. And I'm also going to be using this identity here. The cos of 2A is 1 minus 2 sine squared A. So there's a reason I've picked that one, and I want to be able to rearrange this. Now I know that from this I can rearrange this to get the sine of A squared as 1 minus cos 2A halved. So they're the identities that I'm going to use. Now, I'm going to extend my ideas with those identities. So with those identities, I know also that sine 2 theta is 2 sine theta cos theta. Therefore, sine theta cos theta is a half sine 2 theta. So that's important. Okay. What I'm now going to do is go back to my expansion. And I've got those waiting in the wings. So you can see that what I've got here, this bracket here, is sine 2k plus 1 times theta. So the first thing that I'm going to do is I'm going to rewrite that as sine bracket 2k theta plus theta. So I'm going to consider the expansion, and I'm going to do it down here, of sine 2k theta plus theta. Now I know that that's going to be the sine of 2k theta cos theta plus the cos of 2k theta sine theta. So I'm now going to go back and I'm going to rewrite the whole of this. So I'm going to rewrite the whole of this. So it's going to become sine squared k theta plus, and I've got a bracket here, sine 2k theta. I've accidentally clicked that thing again. That's sine 2k theta, sorry about that. So that's a theta. Cos theta, we can live with that, can't we? Cos theta plus cos 2k theta sine theta. And of course, that all got multiplied by sine theta. And we're all over sine theta. I'm now going to expand out that second bracket. So let's expand out that second bracket. So when we expand that out, we're going to get sine squared k theta. Everything's going to get multiplied by sine theta. That's a plus, by the way. It looked remarkably like an equals. Okay, but it's a plus. So we're going to get sine 2k theta cos theta sine theta plus cos 2k theta sine squared theta. And that's all over sine theta. So hopefully you're still with me. Okay, now if we go back to this identity here, okay, sine squared of an angle is half 1 minus cos 2 of those angles. So what I'm going to do is I'm going to rewrite sine squared k theta using that identity. So that would be a half 1 minus the cos of 2k theta. Okay, so I'm going to rewrite that. So I'm also going to rewrite my sine squared using that identity. So let's rewrite the whole thing. So it's going to become a half 1 minus cos 2k theta plus a half sine 2k theta sine 2 theta plus a half cos 2k theta 1 minus cos 2 theta all over sine theta. Okay, I'm going to a new page now because I think I've done quite a lot of writing there. So I'm now going to take out the factor of a half on the numerator. So I've got 1 minus cos 2k theta plus sine 2k theta sine 2 theta plus cos 2k theta minus cos 2k theta cos 2 theta all over sine theta. Right, what have we got? I can see that that cancels with that, and we can now rewrite this. I've changed colour. We can now rewrite this as a half 1 minus the cos, I'm going to use bracket, 2k theta cos theta, and because I've taken the minus out and that's a plus, minus sine 2k theta sine 2 theta. And can you see my deliberate mistake? She lied. Can you see that's minus cos 2k theta cos 2 theta, and when I've written it there, I've lost the 2. In fact, I don't think I can subtly squeeze it in. So let's go back and make sure I've done that properly. Okay. And that's all over sine theta. Now, what we've got here is cos cos minus sine sine. So if we go back to the identity that we wrote down ages ago, cos cos minus sine sine, we can rewrite this using our cos A plus B identity. So we've got a half 1 minus cos 2k theta plus 2 theta all over sine theta. And what I'm now going to do, I'm going to write a bit smaller, is what I'm going to do. I've got a half 1 minus the cos if I take out a factor of the theta, 2k plus 1 theta all over 2. It's such a lie, it's not all over 2. It's all over sine theta. Let's go back to another identity. We know that sine squared of an angle is a half, 1 minus cos 2 of those angles. So what we can do is, if we have a quick, like similar to what we've got here, we know that this can be written as the sine of the angle squared. Right, can I just go back? Right, what I should have done here is taken out. Can I just, I'm not going to redo it. Let's go back to this bit here. There's no way I'm redoing it. Right, when I take out the theta, I'm left with, that 2 needs to be out, doesn't it? Let's go back. So there's no way I'm going to go back and do that. So I've got 2k plus 1 theta. Now, you know, let's go back to our identity. Sine squared A is a half, 1 minus cos 2A. So using that identity, okay, you can see that A is k plus 1 theta. So that can be written as sine squared of k plus 1 theta all over sine theta. Right, I nearly blew it at the last minute, right, by taking my 2 out incorrectly. Hence, blimey, hence what we tried to prove at the very, very beginning. If we go back, okay, we have shown that this equals that. It's taken absolutely ages. Hence, the sum, and I think I need to go back to the beginning where I wrote it down, still write this down well, k plus 1, r equals 1 of the sine 2r minus 1 theta equals okay, I'll just show that again. I've shown, because I'm proving this for the k plus 1th term, aren't we? So we want the k plus 1 in there, k plus 1 theta over sine theta, which means, hence, it holds, so our result is true for n equals 1. It holds, so if it holds for n equals k, it holds for n equals k plus 1. Therefore, we have proved by induction proved by induction what we were asked to prove, the sum from r equals 1 to n is true for all integer values of n greater than or equal to 1. Such a difficult question. But there was an n bit. So the n bit, so you can see that the angle, so theta here is pi over 7. And that to get the 13 pi over 7, n would have to be 7. So what you would be doing in this last proof bit, sorry about that, so the last bit, so part 2, so what you're doing is you're finding your sum from r equals 1 to 7, and it's going to be your sine and of your 2r minus 1, and your angle is pi over 7. So you're just simply replacing that, aren't you? So you're going to have the sine of 7 pi over 7 all over the sine of pi over 7. And it does ask you for the exact value, but if you put it in your calculator, it is 0. Phew! Right. Here are the questions. Again, they are from your Pure Core 2 textbook. Just move that slightly back so you can see it a little better. So they're taken from your Pure Core 2 textbook. They're quite difficult. So definitely have a look, 17, 18, 19, 20, very much worth a go. You can see that question 21 is really challenging, but the worked solutions are in the back. So these are in your miscellaneous exercise. The worked solutions are in the back and really good. So this is for miscellaneous exercise 1. Use the work solutions in the back. Well done.